What is up, everybody? Chapter 6 review coming up right now. I hope it's really going to be less than an hour. I'm going to be going through this really quick because you should have done the 6.1 through 6.6 already. So these are the topics. We're going to be doing vectors, unit vector, component vector, magnitude, direction vector, physics, force and stuff, dot product, polar equations, parametric equations, sys of x, polar equations, properties, and De Moivre's theorem. Right, we're going to be doing all of those today. So, first of all, what are vectors? Vectors are these little things right here. The little things have the magnitude, and they also have the direction. So, magnitude is the strength of the vector. For example, if I push someone with a small force, then it will be a small magnitude. If I push someone with a big force, it will be a big magnitude. So the length of the vector determines the magnitude of the force. Yeah, it sounds like I'm teaching physics. It's really math. This is the direction is basically just what direction you push it in. So these are vectors. They have a magnitude and a direction. They're not singular. They have two components, right? The singular would be a scalar. That's what they would call it. So vectors. Yeah, I already said that. So finding vectors is a similar way to how you find slope, and how you find slope is not whenever you find slope, you divide by the you simplify, but in this case you don't simplify, right? Because you want to preserve the magnitude. So we have from P to Q. So I'm going to kind of graph this. 2, 5 is about right here, and then 3, 8 is around right here. So if you have this arrow right here, this is our vector, right, from P to Q, and the horizontal component change is 1, and the vertical component change is 3, so our vector is 1, 3. And Q to P is the opposite, is the other way. So Q to P this time, we go from Q to P. So you go down 3 and down 1 this time, so it's -1, -3. Right? You could also visualize it like this, -1, -3. Right? So this way and then this way. We have PQ plus QR. R is 1 minus 10. So let's draw that 1 and then -10. That'll probably be somewhere down there. And then, so PQ plus QR is actually PQ plus Q. Okay, not responding. PQ plus QR is actually PR. PQ plus QR is PR. It's the same way as how you would add together line segments. In this case, it's vectors. So if you have this PQ right here, and then you have this QR right here, right? It's moving down, right? The sum of those vectors is going to be PR. So we could do PQ plus QR, but let's just do PR. So 1 minus 2 is yeah, you have to take this and then you subtract this because that's how you find slope. 1 minus 2 is -1, and -10 minus 5 -15. So it's -1 -15, right? Yeah. Okay. Yeah. So 2QR minus 3QP. First of all, do we have QR yet? No, we don't, so we gotta find QR. So QR is equal to 1 minus 3 minus 2 minus 18. So 2QR, 2 times this. That's how you do our linear, the combinations, right? The linear combination. That's what they say in the book. So it's -4 minus 36. And then QP minus 3QP, we already have QP, so minus and then minus 3 of them, so that would be 3 minus 3 minus 9, which adds up to -1 minus 27. And this is our vector of 2QR plus minus 3QP. Okay. Next, component form of a vector. I've been using the component form of the vector, as you could see. This is the component form of a vector right here. The component form of a vector is a, B, where A is the amount that you move to the right, and B is the amount that you move up. So in the this V1 right here, 2 comma 5 is like moving X and moving Y. So 2 up, 2 right, 5 up. 3, 4, I should have put this kind of before the page 3, but whatever. 3, 4, 2 plus 3, 5 plus 4, and then 2, yeah, this is how you do the combinations. You can take v1, add it to itself, or you can take like half of v1, and they would all still be a vector. However, multiplication is a little bit different. I'll tell you about that later. This is the algebraic proof that a and b, whenever you take this a and b and you decompose it into this other form, which is the I hat j hat form. The I hat is the unit vector, is the one unit vector. That's why it's called the unit vector, because it only has a side of 1 in the x direction, and j hat is in the y direction. So a times I hat plus b times j hat, it can also be written as a bracket a comma b bracket. And this is the algebraic proof of the plus rule and that it works, right? So if you want to stop there, you could. So we have express 17 over 20 as a unit vector and find a component. So this is a little bit, I didn't really give you any formula, I did give you an example. The magnitude of a vector is found by finding the distance of the vector. So this vector has a distance of square root of 689, so distance is 689, but our goal is to have it so that the length is only 1. So if you want your vector to have the length, if you want the length of the vector to be only 1, you have to use this formula right here. I don't want you to memorize the formula because it's really actually pretty intuitive. You just take the whole vector and then you divide by the magnitude, because then if you have let's say you had a vector of length 3, right? Let's say this vector was length 3 instead. You divide it by 3, you'll have a vector of length 1, unit vector. You want a unit vector. Unit vectors are really important because they represent direction. So 17 over 20 over square root of 689 gives you a unit vector. 17 over square root of 689, 20 over square root of 689. You can set our cosine and sine to these unit vector components in order to find the x and y. So the neat thing about this is we have this cosine right here, and if I drop this down and we had a unit vector, it will be opposite over hypotenuse. Let's say, okay, this is not like a good scale, but let's say this is 1, right? So this is 1, this is y, this is x, right? So if we had our cosine theta is x over 1, right? Cosine theta is x over 1, which is 17 over square root of 689 over 1. So to find theta, you just take the cosine inverse of 17 over square root of 689. You get 49.6 degrees. Or you can also do tan inverse of 20 over 17, and that will also get you your 49.6 degrees. So this is a simplification. It actually looks a lot more messy. So v, if you want to take this v vector right here, the v vector is decomposed into 2 components. This component of the vector will be v cosine theta, and this will be v sine theta. So v cosine theta, v sine theta. This is u, and then if you condense the v into u, a unit vector, right, which is v with a dash through it, and then divide it by its magnitude, you will get cosine theta sine theta. You will get the angle. Cosine theta I hat plus sine theta j hat. Okay, the effect of gravity. This is a little bit confusing. A little bit more confusing. What is the force of the gravity acting on the box? In this case, we have a 40 Newton box. 40 Newton box going this way. If we have the 40 Newton box going this way, our G, our G, which is the force of gravity right here. If you take G and then sine of the 10 degrees, sine of the 10 degrees, because our thing runs horizontal. This is our plane. So if you take the sine of the 10 degrees, you will have G sine 10 is equal to 40, which is this, right? So 40 is equal to G sine 10. So G is equal to 40 over the sine of the 10 degrees, which is equal to 230 newtons, right? So in this case, now we have our G. G sine 40 is equal to our force, which is 25 kilograms. Our weight, which is 25 kilograms. I should put. I'm gonna annoy a lot of people who do physics because I didn't put a weight here. I should have put a weight here instead. 25 kilograms of constant force, and then G is equal to 25 kilograms over the sine of 40, which is roughly equal to, I think, about 27. The 25 divided by the sine of 40. 25 divided by, no, not 30 degrees, sine of 40 degrees, is roughly 38.89. 38.89 kilograms is the force of the gravity for this one, right? And why does this work? First of all, when I first looked at it, it seemed a little bit confusing because it really was a little bit confusing. We had this 40 right here, and then if you had this sine, if you did the cosine 10 to this 40, it's like G cosine 10 equals 40. You will be finding this line, the force, the horizontal force rather than the vertical force. However, if you had a G this way instead, if you had it this way, actually you shouldn't. I don't know what I did. I don't know what I did with this. This isn't even supposed to be the equation. The equation is just 40 sine of whatever. So this is our 80 and this is our 10. So this will be cosine 80 because this touches this vector at 80. So cosine 80 is the same as sine 10. And it works because it touches the vector, and this is v cosine theta, v sine theta, and it's kind of the same, but just flipped the other way around. So you could say minus 230, and as well if you're talking at vector terms. So dot product, dot product. First of all, dot product is if you take the vector u, and then you dot product with the vector v. You multiply the first term with the first term, add it together with the multiplication of the second term, add it together with, if there's a third term, fourth term, fifth term, you keep adding them. But in this case, we only have these two terms right here. So this is our dot product for now. It does satisfy all the properties, commutative, associative, and distributive properties. Actually, it doesn't satisfy if you do this, but it does satisfy if you do this. Right, if you just switch the vector's position, it does, but if you switch the numbers in the vector, it won't satisfy the distributive property. So, no, the associative property, and pretty much any other, pretty much the commutative property as well, because, well, it gives you a different answer. So, distributive property, also works. So if you take u and then u dot v like this, you'll get u. No, you'll have to do the u and v first. You will have to. So honestly, I just put this distributive here just for, I don't know, for show or something, but it works in some cases, because you'll actually have to solve the u dot v first before you even get a chance to solve the u, unless if it's a magnitude, that would be easy. If it's a magnitude, I think it will satisfy the distributive problem. So one of the most important theorems of this chapter is the angle between two vectors theorem, and it's the worst name ever, right? That's why I said it was the worst name to ever be given to a theorem, because it's such a bad name. U dot v is equal to u v cosine theta, right? And I could prove this using law of cosines. If you guys want to prove it, put it in the comments. I'll pin your comment. Using the law of cosines. So if you solve this in the comments, clue, it's something to do with a parallelogram. Does it? No, that's cross product. I'm sorry. So just use the law of cosines and try your best to prove this theorem. U dot v is equal to u, v, and cosine theta if the theta is 90 and they are orthogonal, and u dot v is 0 degrees. So that's how you prove the perpendicular. Next is projection from vector 1 onto vector 2, which is a little bit confusing. Projection from vector 1 into vector 2. This is wrong. Right? Replace all the projection VUs you see with projection UV. Projection UV. Wait. I think it's actually correct. Yeah, projection of vector V onto vector U. Yes, that should be correct. If you want the projection, you gotta find first of all, the projection is basically doing the same thing with finding the x and y components, but you just do it to a vector. So instead of finding a x and y component, you're finding the vector component. So in order for you to find the vector component, you will have it as the magnitude of the projection and the direction of the projection. So if you want to find the magnitude of a projection, it's just v dot u. You can find this. You can use this formula for v dot u equal vu cosine theta, and then you can do this. I'm dying. Okay. You can divide it by the magnitude of u in order to get v cosine theta, and the v cosine theta right here, the v cosine theta is basically the projection of v onto u, because we have v here and then we have the cosine theta, right? This is v cosine theta and this is v sine theta, right? We've already gone through that. And then the u is just the unit vector is just u divided by the magnitude of u. So then your final formula will be this, but you can actually simplify it and you can put it like this, right? V dot u times u over the magnitude of u squared. And that is, right? Okay, the book doesn't actually put these arrows on. I like putting the arrows on because that shows it's a vector, not like a variable. So this is our formula right here for projection vector 1 into vector 2. And I think there's questions now. Okay, 6.2, question 22, 47, and 65. Question 22 gives us a vector 3, minus 3, comma 8, and another vector which is minus 1, comma 9, and ask us to find the angle. Minus 1, comma minus 9, minus 1, comma minus 9. So I asked us to find the angle. So in order to find the angle, use the angle between two vectors theorem, add them together. This will get me minus 69, I think. Yeah, minus 69 equal square root of 73. Yeah, I'm not gonna add the square root of 73 multiplied by square root of 82. I'm really sorry about the outburst. And then take that divided by take that multiplied by the cosine of theta, and you take the minus 69 divided by the combination of these two, which I don't even know what 73 times 82 is in my head, but just do this, put the theta, and then put the cosine inverse, right, or the arc cosine, right? So this is our angle right here, whatever it is. 47. 47. So 47 is braking force. A 2,000-pound car is parked on a street that makes an angle. I'm gonna skip 47. Wait, actually, should I? Nah. Should I skip? No, I'm not gonna skip 47 because it's actually important. We have this right here, and then I'll substitute it for No, I won't. Okay, so we have this right here, and we'll make 12 degrees right here, and then here's a car. I can't draw a car. Right there. Right, that's a pretty okay car. And it's going this direction, obviously, from this slope. So what they're trying to say, what they're trying to do is, we have to find the magnitude of this car. We have to find we have to find the direction that it has to go the other way in order for the car to not roll down the hill, the force, right? So I've actually worked this out in the homework. So our vector going this way, is, no, our vector going this way right here is cosine 12, sine 12, right? This is our unit vector. So actually, I'm gonna put the unit vector right here. Unit vector is cosine 12, sine 12, right? So we're gonna be using the projection, because here we already have this, and then this is our minus 2,000, because it's a 2,000-pound car. It's exerting 2,000 pounds onto the earth. That's why it's called a 2,000-pound car. That's how weight is defined, I think. So we're gonna be using projection. It will be u dot v. So this is, let's say this is f, actually, f. So f dot v over v squared times v. And since it's a unit vector, the v really doesn't count. So we'll end up having minus 2,000 multiplied by the this vector right here is 0 minus 2,000, because it's going down in the y direction. So this will end up being 2,000 sine 12, and then multiply that by the, I need to be able to think. Multiply that by cosine 12, sine 12. And in order to find the magnitude of this, you can just take the magnitude of this. No, you can actually, yeah, you can just take the magnitude of it. It's not that hard. So just multiply these into here, and then square it, and then divide it. And the magnitude that you should get is 2,000 sine 12 minus 2,000 sine 12. This is probably what your magnitude is going to be. It might not definitely be, because I just go really fast, and I don't actually do the homework that properly. So there you go. Okay, actually no, we're not done yet. Looks like this is going to last more than 1 hour. 65. Which of these is equal to projection of v over u? We have u is equal to 3 over 2, minus 3 over 2, and then we have v is equal to 2, 0. So projection of v onto u, no, projection of u onto v, u onto v. So we'll have u is our 3 halves, minus 3 halves. So we have 3 halves multiplied by 2, minus 3 halves multiplied by 0, which doesn't really count. And then we have our v squared right here, v squared, so that's 2 squared, that's 4. And then multiply that by our 2 comma 0, our vector. All right. So we have 3/2 times 2, multiply by 2 again. That will get you 6/4. So this is our final vector is going to be. Wait, let me see if I did this correct. Let me see what answer did I give. Yeah, I gave A. So 3/2 comma 0. Right? 3/2 comma 0. Yeah. Next up we have parametric equations. These are quite important. The paramet I farted. These are quite important.
He farted.
To
Yeah.
be able to define, as in these are quite important. Okay, this is just becoming a rugged mess right now. So this is really important in order to define a like a position easier. I can't speak English. This is a form of x and y, where x and y are independent of themselves. Although if you substitute the x for the t, the x and the y, right? X and y are in another function t. But if you substitute the x and the y, since they're in another function t, they will still be continuous if they get connected back together. So x of t will give you this initial point right here. There's an initial point, and plus x comma t plus x plus the function, and y will be y and then plus the function, obviously. So why do we have parametric equations? Well, I'm gonna showcase it right now. So let's say our initial point is right here. This is our initial point right here. So our initial point will be working at 0 comma 0, and then this will be at x of t comma y of t. Right, so x of t comma y of t. So we're trying to find the path of a rotating circle, one point in a rotating circle drawing a path. What are our x of t's and our y of t's going to be if we try to find those paths? First of all, if you notice that there is a point down here, and if you want to rotate it, the point starts right here. It starts right here. It doesn't start right here. If it started right here, it would have been easier because I could have just done cosine and sine. But since it's starting right here, I'm gonna actually rotate this so that it starts right here this time. So right here. So let's pretend for a second it starts right here, because we're gonna be rotating the other side. We're gonna be rotating the other way anyway, so it doesn't really matter. Doesn't really matter. Okay. So if we rotate it this way, then it would have been a it would have been a cosine and a sine. X of t equals cosine, and y of t equals sine. But since we're rotating the opposite way, right? We're rotating it we're rotating it the opposite way. Everything is going to be negative. So minus, this is going to be minus, and this is going to be minus for our function. For a function. So minus, actually, I don't even know why I had these. Minus, and since we're starting down here, everything's also going to be shifted back 90. Shifted back 90. So we have this graph right here, and we have sine. Actually, no, we have negative sine. Right? If you shift this back 90, you'll have this. So then you'll end up having negative cosine. This is negative cosine of t. And then if you shift your negative cosine, if you shift it back a little bit, you will end up having Wait, negative cosine shifted. They'll end up having positive sign, I think. Positive sign. Right, so that's our, no. The x coordinate is our positive sign and the y coordinate is our negative cosine. Okay, I think I'm messing this up terribly. Let me look it up. So circle, cycloid, parametric equation. That's called a cycloid. Yeah, no, wait. So they'll be both negative. They'll be both negative, but this is supposed to be negative sign. I'm sorry. Does it our x position starts from the minus, right? It starts down here and then it goes up. So this is supposed to be negative, and then our y position, no, our cosine, the y position, starts from here. So our y of t will never be, you could see that our y of t will never be moving. Our bottom, the bottom of our y of t is 0, and the top of our y of t is 2. And so therefore our our function will have, oh god, I'm sorry, will have an extra thing of 1 right here. So this will be 1 minus cosine of t. What about x of t? So what will we have for our x of t? X of t actually does move dependent on time, right? So x of t does move dependent on time this time. So we will move it dependent. We'll move it on time because every single time you move, this is assuming that the circle rotates at a pace of 1 radian per second. Every single unit time that you move one circumference, you'll get 2 pi. You'll get the arc will be 2 pi long, and that's what we want. So we want the arc to be 2 pi long every unit time. So that's how it will work. That's how the x position will work, x of t minus sine t, and then y of t will be 1 minus cosine t, since it can never get above, it can never get above, and our cosine is already at 1, so our point can start at 0. Okay, let's graph some some fun parametric equations. And we're gonna graph all of these in the interval t is 0 to 2 pi. 0 to 2 pi. Actually, yeah, we're gonna graph this in the interval t equals 0 to 2 pi. These will be 0 to 2 pi. But then the top I'll graph in the interval 3, 0 to 5. So how do you graph? You can make a point, you can make a table of values, or you can just put x in terms of y. And that's what I'm going to do, right? So I'm going to put x in terms of y. This is y minus 5, and then over 3, and that's equal to your t, right? So t is equal to y minus 5 over 3. Now I can put this in here, x equal 2 times the y minus 5 over 3. And take this all squared. You multiply it, you have 2 times y squared. I'm gonna take the 2 over 9 outside. 2 over 9 times y squared minus 10 y plus 25. Right, and that's going to be our function. Or we can leave it as 2 over 9 times y squared, y minus 5 squared. Now I know the teacher doesn't actually like bad graphs, but I'm just going to make a bad graph anyways. Look something like this. Alright, so it's going to look something like this, pretty wide. I made it pretty wide. But that's what the graph's going to look like. That's how I'm going to make it wide. So what about x equal 2 cosine t and y equal 2 sine t? Now this is amazing because we already have our two cosine t's and our 2 sine t's. I'm actually going to first of all restrict this for a little bit because when you have 0 in here, as in when our, wait, is this x equal y? This is x equal y. This is x equal y, not y equal x. I'm sorry. So since this is x equal y, you'll have 1, 2, 3, 4, 5. It'll be around right here, and then it will be something like this. And actually, I don't want to draw the 2 arrows like this. Some people do, and I think you will be advised to draw it like this, but I like to draw it like this to prove that the projectile is moving through time, right? So t. So what about 2 cosine t, 2 sine t? This is easy enough, because cosine t and sine t are basically just our circles, our unit circles, where cosine is x and sine is 1. So we could just do this and it will work, right? Make sure the radius is 2 though, or else it obviously won't work. Okay, what about if our x is 2 sine t this time and our y is 2 cosine t? So it's switched. Now the fact of the matter is, if it's switched, what you can do is you can switch the whole graph by itself. You can literally just switch the graph to account for that x and that y, right? So we're gonna put 0 right here. We're gonna see how we can switch the graph. So let's put t equals 0. T equals 0 will give you x will give you 0, and y will give you 2. So it'll be 0. Where is it? Yeah, x will give you 0, y will give you 2. So it'll start from up here, and then 1. Oh no, let's try pi over 2. Pi over 2. So sine of pi over 2 is what? Sine of pi over 2 is 1, and cosine of pi over 2 is 0. So it'll be 2, 0 now. And then let's try pi. So this is at 0, this is at pi over 2. Let's try pi. So 2 sine of pi is 0, 2 cosine of pi is negative 2. So it'll be right here. And you could see that if you plotted more points, you could see, okay, that is terrible. You could see that it will also plot a circle, this time starting from right here. So this is our starting point instead, right here. And this is our starting point right here. So it starts here, goes this way, but in this case, it starts here and goes the opposite way. Right? It's a very, very interesting phenomena. It starts here and goes the opposite way. If you switch x and y, it will go the opposite way. Right? I actually did not know that before I did this lesson, before I looked at this. So we're going to do question 49 from 6.3. I hope it's not too hard. I don't want this to last too long. Question 49 from 6.3 is hitting a baseball. Orlando hits a baseball when it's 4 feet above ground level with initial velocity of 160 feet per second. The ball leaves about at a 20-degree angle within the horizontal and heads towards 30 feet fence, 400 feet away from the home face. How strong must the split-second wind gust be that acts directly with or against the ball in order for the ball to hit within a few inches of the top of the wall? What the heck was just said? Hits a ball when he is 4 feet above ground level. So right here we have our ball right here, which is 4 feet above ground level. And it has an initial velocity of 160, and the ball leaves at 20. So our initial velocity, and it leaves at 20. So it will be like this, and it leaves at 20. Right, it's 20 degrees and 160 feet per second. And then it will have it will head toward a 30 feet fence, 400 feet from home plate. So let's say this is a fence right here. And I actually don't know if the 30 feet fence is 30 feet horizontally or 30 feet vertically. So how strong must a split second wind gust be in feet per second to act that acts directly with or against the ball in order for the ball to hit within a few inches of the top of the wall. So this will be 30, right? This would be 30, because it's saying the few inches now, so 30 feet, and we want it to hit like around right there, right? Around right there. It's very inaccurate, right? So our initial our physics physics our physics understanding, I say, will give you that the x coordinate is equal to, if you even know this from physics, our x coordinate and our y coordinate is just going to be the gravity, the initial velocity from which is 160 sine t, right? The initial velocity 160 sine t. We don't really even need the x, 160 sine t, and our y will be our deceleration, or going down, will be minus 16 t squared, right? Minus 16 t squared, or minus 32. Is it minus 16 or minus? Yeah, it's minus 16 t squared. So our x will be, this time it will be 160 cosine. Actually, this is sine 20. Minus 16 t squared. And then our x will be 160 cosine 20. But this time it's our x is not influenced by the time. This is actually 160 sine 20 160 sine 20 t, I think. So this is, our x is 160 cosine 20 t, but it's not really influenced by any of our variables, assuming that there's no wind. So basically, what we're trying to say is, what extra c value do we have to add to our our x, in order for the y to land right here, which is around 20, let's say 25 feet. So let's say 25 feet. We want our y to be at 25 feet by the time that we get. So this will be 25 to 30. Honestly, I don't know why I chose this problem, because I don't know how to solve it. I don't. I don't know how to solve this. 160 cosine 20t, and the feet is 400 away. Actually, maybe I do. So it's 400 away. So 400 equal 160. Blah blah blah. Yada yada yada. So cosine 20t is equal to 2.5. Right. So t is equal to 2.5 divided by cosine of 20. We have our t. We have our t. But actually, we don't really have our t yet, because we need to put the t somewhere. We need to put the t in terms of the plus c as well. So I'm actually going to subtract the c. So it's 400 minus c this time. 400 minus c. So then it will be 2.5. 400 minus c. So it will be 400 minus c over 6. 400 minus c over 160 divided by the cosine of 20, which is this is our t. So then you can actually take this, and then you can put it into, there is a shorter formula for this. There is. So then you can put this into the y function. Now we have y is about 25, and then you can solve for c. So 25 is equal to 160 sine of 20, and then multiply that by this whole junk of 400 minus c over 160 cosine 20, and then minus 16 t which is this again, squared. 400 minus c over 160 cosine 20 squared. So this will give me this is how you solve for c. Let's actually go up and solve for it. So I'm gonna simplify this side first. First of all, 160 and 160 is gone. 16 and 160 is kind of gone as well. 160 and 160 is gone. 16 and 160, this will become 1, this will become 10. So then now we'll have actually I can't do that. I can't do that. What's wrong with me? This becomes 1600. 1600. So then now it'll be 400 minus c squared over 1600 cosine squared of 20 minus just regular 400 minus c, so tan of 20, and then times 400 minus c. So expand it all out. We'll have 400. We'll have a really big number. I actually I wanna expand it all out, but I really don't as well. Because this is gonna be a mess. 400 minus c, so it'll be c squared minus 800c plus 16,000, and this is all under the 1600 cosine 20. 1600 cosine squared 20, and then we add this to the wait, where'd the plus come from? It's supposed to be minus. It's supposed to be minus. And then we add it all to the this. So I'll add the 1600 cosine 20 down here as well. So then it will be 1600 cos 1600. This is painful. I'm just gonna leave all of these in terms of regular things. So it'll be 1 over 1600 c squared minus 1/2 c, so minus. Actually, this will be minus, so all of these will be minus 1,300, 1 over 1600 c squared, plus. No, I'm not. I'm done. This is ridiculous. If you solve for c, I will pin your comment again. Solve for c, please. This is. I'm pretty sure this is correct. You have to put the c in, and then you have to do the stuff, and you could like kind of graphically analyze it, but this is ridiculous. No way. I'm not doing this. Polar coordinates. Okay, so this is the next part of the review. I'm pretty sure you already went through this pretty heavily in class. So polar coordinates is magnitude. There's a magnitude and direction, obviously. But in this case, the magnitude and the direction is just the magnitude and the direction. That's the x and the y, right? In x, each of them has a magnitude and a direction. Magnitude and direction. But now, magnitude and direction is just magnitude. It's right there, and direction, it's right there. There's no x and y anymore. X and y, in some cases, x has a magnitude and direction by itself, and y has a magnitude and direction by itself. So you have to change your mind into not thinking like there's a rectangular thing, but instead a circular thing. And this is our graph of r equals theta, which is what the two things that we're going to be using is r and theta instead of x and y. So y equals x, no, r equals theta. So this is how the r equals theta spiral is. Whereas when we had y equals x, it'll just be a straight line on one of these. And these are 4 really important formulas that you should click right now. And I'm gonna move on. So find the polar coordinates of -1 and 1. Now I'm gonna show you a really easy way to find the polar coordinates that doesn't involve any like hard math. -1 and 1. What's -1 and 1 on a regular graph? It's -1 and 1. Right here. Right? -1 and 1. Now let's think polarly. What's -1 and 1 as in degree? We have right here we have 1 and 1, right? Minus 1. Well, this is minus 1 and 1. What's the minus 1 and 1 in degrees? It's 135. Spoilers, 135. And then the magnitude, square root of 1 squared, square root of 1 plus 1 squared is square root of 2. So the polar coordinates are square root of 2, 135 degrees. 5 over 3. This actually does require a little bit more math, but you could just do this, and you have 5 and 3, so 5, 3 would be something like this right here. This is 3, this is our 5. So our coordinates are inverse tan of 3 over 5, which is our angle, and our simple magnitude is just square root of 34. And minus square root of 2. Next is minus square root of 2 over square root of 2 minus square root of 2. This can also be found very simply. You just take the minus square root of 2, then now you have minus square root of 2 minus square root of 2 right here. And what's the angle? Since they're both the same, it's 225. It's 225 degrees. So our angle is 225 degrees. But what's our magnitude? Our magnitude is this squared plus this squared, which is 2. That's it. 225 degrees. So that's how you think polar coordinately. You want to find the magnitude and direction of everything. Magnitude, direction, magnitude, direction. How far apart are the airplanes with polar coordinates? These 3, 110. Let's draw first. 3, 110. 3, 110. So it'll probably be right there. 3, 110. Right? And then 4.7240. It'll probably be right, I'd say right there. 4.7240. So 3, 110, 4.7240. So how far are the airplanes? How far is it in the middle? So what you can find is this, since this is 110 is 240, this is 130. So you can use the previous chapter's law of cosines in order to find this length right here. So you'll have c squared, and actually no, I'm not even gonna bother with c. C is equal to square root of 3 squared plus 4.7 squared minus 2 times 3 times 4.7, and then you multiply that by cosine of the 130, and that is your angle. No, that's your c. So that's your far apart, right? That's how far apart it is. This is the same thing. I was supposed to say how far apart are the two lighthouses. 4 with 12 degrees. 4 with 12 degrees right here. And then 2 with 72. 72. So we had this. And if you didn't notice already, that's a 60-degree angle. That's pretty neat. Pretty neat angle. If we have 4 with 12 and 3 with 72, 2 with 72, let's calculate. All right, we have c is equal to 4 squared plus 2 squared. So square root of 4 squared plus 2 squared, that's square root of 20 minus 2 times 8 times cosine of the 60, which is just 1/2. 1/2. So that will be equal to square root of, very nice number. No, it's not that nice. It's 12, which is 2 square root of 3. And that's our final answer. 2 square root of 3. So then this is actually a right triangle if you haven't noticed already. 2 square root of 3 and 4, that's a 30, 60, 90 triangle. Pretty nice. 17. So this is how do you change the equation to polar form? You can look at this example, but basically the three most important things are x equal r sine theta, y equal r cosine theta, the other way around, sorry, x equal r cosine theta, y equals r sine theta, and r squared is equal to x squared plus y squared. Those are the three most important things. X squared plus 3 y minus 4, that's r squared cosine squared theta. plus r sine theta, 3 sine theta plus 4 equals 0. And what we're trying to find is r in terms of theta. So move everything over there. You will have r is equal to the square root of minus 4 minus 3 sine theta over cosine squared theta. And this is an impossible graph. I think I just made an impossible graph, I think. Yeah, this graph doesn't exist. Does not exist. However, this graph does exist. Actually, this graph just doesn't exist. This graph doesn't make sense. The reason is, even if you had a sine theta that was big enough to counteract the you can't have a sine theta that's big enough to counteract the effect of the 4, and so there will be no value that is bigger than 0, which means or 0 or bigger, which means this graph is null, doesn't exist. It'll be imaginary. What about this? So 3 sine theta plus 9 cosine theta. First of all, what we can do is we can actually take the 3 out here. We can put the sine squared theta plus the 3 cosine squared theta equal r. And if you take the x and the y, actually, what am I even doing? I don't even know what I'm doing. X equal r cosine theta and y equal r sine theta. So this is already a valid graph. We just want to convert it to x, right? Right? Yeah, but this isn't. You know what? I think I messed up on this. You would divide this by r. Okay, so it's sine squared theta. It's simple. If you have this sine squared theta, this is a 3 sine theta, but it doesn't actually go. It doesn't actually go anywhere when we're talking in terms of r. You could do theta is equal to tan inverse of y over x. So what we could do is put this as 3 sine squared of tan inverse of y over x plus 9 cosine squared of tan inverse of y over x plus r equal square root of x squared plus y squared. Pretty sure there's a better way to do that, but that's the best way. That's the best way I can do it right now without wasting all of your time. So theta is also equal to the tan inverse of y over x. If you haven't looked at the other thing already, this works as well. I should have put the r as r squared, because now it isn't really a circle anymore. So that's basically the implicit equation. I don't think you can actually solve in terms of y or x for that. That's pretty hard. Find the maximum values for these graphs. So now we actually have like our graphs, our pure graphs now for our polar equations. So if you take these polar equations, 3 cosine theta, what's our maximum value of 3 cosine theta? This is how the graph looks, right? How the graph looks. So the graph looks kind of like this. Let me use a different color. Oh god, it's a pretty nice graph. That's how the graph looks like, right? So it looks pretty nice. But what's the maximum value? Well, the maximum value is just when theta is equal to 1, right? So that's just when cosine theta is equal to 1. So that's the maximum value of the theta anyway. The maximum value is 3. This has 2 times sine theta plus cosine theta. When is sine theta plus cosine theta maximized? It probably doesn't come as a shock to you to find out that it's maximized whenever both of these have enough of their components in order to give it the greatest value, and they both do at the value of 45 degrees. So this will be square root of 2 over 2, this will be square root of 2 over 2. You have 2 square root of 2 over 2, and so it is 2 times square root of 2. That is our maximum value. Find maximum values for R values and for which data the R values are. So we're trying to find the data where the R values are maximized. So we just have to find when this is equal to 1 and this is equal to 1. What's 3 times minus 2? I think I was drunk when I made this. No 3. So theta can be 0. It can be pi over 4. It can be 2 pi over 4, pi over 2. So it can be basically anything, pi over 4k, or pi over 4n. For this one, theta is 0 whenever it's pi over 4, 3 pi over 4, and then, yeah, etc., right, 5 pi over 4. So it can be at any value that is 2 times pi over, or pi over 2 minus pi over 4k. And first of all, what are the maximums? This maximum is minus 2 and this maximum is 3. You can see clearly from the graph. I think the graphing part's coming soon. I really don't want to do it. Yeah, this is graphing. So you already saw this graph. So I actually don't have to try that hard on explaining to you why this graph works. It does work. So the graph just looks like this, right? Because it gets bigger as data goes over time. This is not accurate, but whatever. But let's try the sine 3 theta graph. I already showed you what sine 3 theta. This is not what 3 cosine theta looks like. I'm sorry. This is not what sine 3 cosine theta looks like. This is like cosine 3. This is like sine 3 theta, not 3 cosine theta. Right? This is, yeah. So basically, the graph that I just showed you was this graph right here. So it's 1/2 square root of 2 over 2, square root of 3 over 2, 1, square root of 3 over 2, square root of 2 over 2. So basically that's one petal. And then after that it goes to the negative. But it goes to the negatives. If it went to the negatives, it would be like this. If it didn't go to the negatives, it would be like this. But since it's to the negative, it actually goes the other way. And that's why there's this orange petal right here. Since it's not negative, right? So in this case, 2 cosine 2 theta. What's this going to give me? We have square root of 3 over 2, square root of 2 over 2, 1 over 2, 0. So basically, our first petal is just it's just regular, right? Square root of 3 over 2, so it starts right, I think, pi over 12. So 0, it starts at 1. Actually, no, these are doubled, right? So I don't even know what I'm doing. This is square root of 3, this is square root of 2. So it's supposed to be 2, square root of 3, square root of 2, 1, 0, minus 1, minus square root of 2, minus square root of 3, and then minus 2. So it starts at 2, and then it goes kind of right here, and it goes kind of right here, and then at pi over 8, it goes to square root of 2, so it goes like right here, and then at pi over 6, it goes to 1, so like right, okay, I need to draw this better. So like right here, and then at pi over 6, it goes like right here, and then pi over 4 is 0, so right here it's 0. Right, so I'm assuming that it's like it's something like this where it goes like that, right? And then we have pi over 3, it goes minus 1. And pi over 3, where's pi over 3? It's right here, but it goes minus 1. So even though we have 1 over here, we have to put our minus 1 over here. Then our minus 1 will actually be going down here. And so we have this pi over 2. Even though the angle keeps going up this way, we have to extend this all the way till we get here. And then if you haven't predicted it by now, it will go like this, like this, like this, and then it will go back. Right, so it'll go like this, like this, like this, and then it'll go back. So it's a pretty interesting. This is 4 clover. this thing has 4 clovers, and reason it has 4 clovers is because of the symmetry situation that you have when you have your even. If you have an even, you have 2 times the even number of petals. Odd just makes 1 times the number of petals. So graph all of these functions for me. Just use your paper. I don't know. I'm not gonna graph it because I'm too freaking lazy. Clue. One of them look like, I don't know. One of them looked like this, something like that. Yeah, graph all of them for me. Yeah, graph all of them for me. So I'm gonna explain to you what these graphs are actually first. So generalization. This is a generalization of all the graphs. So we have this, a number plus, and then the number plus another number, sine theta. If it's sine theta, it'll be up or down, and if it's a cosine theta, it'll be left or right. So the loop in between those graphs, and if you graph it, you'll understand what the loops are, right? So a over b, if it's smaller than 1, then the loop is, so this over this smaller than 1, so R3 for example, you will get like a knotted loop. For equal to 1, if it's equal to 1, then you'll get a concave undifferentiable loop. If it's between 1 and 2, you'll get kind of a smooth loop, a smooth bump, and if it's 2, it'll be convex. So it won't be concave. So I'm actually just kidding. You don't actually have to graph it. Right here, those are all the graphs. You could see that the R3 has a loop, the R2 doesn't. The when it's a equal to 1, but it does have like a strict springy yeah, and the R4 has a small bump, but it doesn't have a loop at all. And then the R1 is the biggest. No, the R1 is the smallest, I think. But it's actually, it looks like a circle, even though it's not. It's a convex Limason curve, right? It's called a Limason curve or Limason curve. I don't know, but it's not. It's definitely not a Limason curve. So Limason curve, because it's a French name. So let's graph some of these functions. R squared equals 16 sine 2 theta from 0 to 2 pi. So what's 16? Okay, first of all, we have this is R squared is equal to 16 sine 2 theta. So our square root is going to be R is equal to 4 sine square root of sine 2 theta. Now, since there's a square root, we actually have a domain now. Our domain is, it can be 0, right? That's totally legal. So at 0, it will be 0. It can be all the way to pi over 4. Now, it can be all the way to pi over 2, in fact, because all the way up to pi over 2, it's all the way up to pi over 2, it has pi, right? So then it's positive, it goes to 0, so sine all the way up to pi over 2, and then pi over 2 to pi doesn't work. But then we have ourselves another example, another set, which is pi to 2 pi, 3 pi over 2, 3 pi over 2, right? And then that doesn't work, and then finally we have our final value, which is 2 pi. So that's all the graph. Yeah.
Con ăn bún chả giò hay ăn mì xào giống người kia?
Ăn bún chả giò.
Ăn bún chả giò.
Okay, so these are two, but when you have them move up to when you have them move up from 0 to, let's say, pi over 6, right? You'll have pi over 3. So pi over 6, you'll have pi over 3 in here. Sine of pi over 3 is square root of 3 over 2. You'll have 2 square root of 2. 2 square root of 2 for pi over 3 is about right here. Let's say you have another thing, which is pi over 4. Now it's pi over 4. You have your maximum at right here, and then it's gonna go down from there, right? So it's gonna go down here, and then you'll have your first loop right here. So it'll be something like this, and like this. So your first loop will be something like this, right? And then what will happen after? Nothing. That's yeah, nothing will happen. If you have pi, let's add pi in there. If you have pi, you are essentially creating another loop, like the same loop. You're essentially creating um another loop, but this time you kind of rotate it 180 degrees because you start at pi. Instead, this is pi. So if you have pi here, you'll be starting this same loop right here, like this. And there's a name for this curve. I just didn't write it down. I don't know what it is. But this is our curve right here. Our 16 sine 2 theta, where this is 4, this is 4, right? The maximum is 4. This is not 4, because I threw it terribly. So that's 4 and that's 4, and this is, honestly, I could draw the circle to illustrate that it's a polar graph, not a regular graph, but that's what we have for our curve right there. That's how it's gonna work. So we're gonna go into a final part of the review. 1 minute, 1 hour 11. Complex number can be written in its trigonometric form as well, and you can read this to try to understand why it's our trigonometric form. Because there is a unit vector. See, so all vectors have magnitude and direction, and here's our magnitude and direction, and that's how you find the trigonometric form of a complex number. There's a bunch of rules. Whenever you multiply complex numbers in together, you add their angles and you multiply their magnitudes, right? So that's our rule right there. Add angles, multiply magnitudes, and same thing with divide. You divide the angles, and then you multiply the magnitudes. No, you don't divide the angle. You divide the magnitudes and you subtract the angle. There you go. Okay, so that's all the proof. If you want to actually look over them, then sure, you can look over them. I don't even know what this is. What is this? I don't know what this is. So anyways, for the complex number z to the, this is called De Moivre's theorem. De Moivre's theorem states that for the complex number z raised to the nth power, the trigonometric form of that answer will be z to the n power equal r to the n times cosine of n theta plus I sine n theta. And you could derive that from the multiplication rule quite easily. And we are going to try to find now we're going to try to find some roots of complex numbers. Now, finding roots of complex numbers is really easy if you know this if you know the unit circle trick. And you probably won't be allowed to use this on the test, but the unit circle trick is the easiest way you can find the roots of the complex numbers. Have this circle right here. So the roots of the complex numbers, whenever you are describing something in terms of trigonometric, like trigonometric turn, right, with the cosine theta and the I sine theta, when it has direction, every single time you add something into it, every single time you multiply the thing, you are adding something into it. So every single time you add something into it, you are turning the thing more. This will become 100. Okay, so how many times? I'm gonna ask you a question. How many times do you have to turn? Like what's the degree measure? You have to turn 3 times to get to 360. The answer is obviously 120. So this is one of our vectors. We already found one of the roots. This is a root. The magnitude's 1, so it's 1 times cosine of 120 plus I sine of 120. Boom, done. You can work this out. You'll find out that this is the square root. Is it? No, it's minus 1 over 2 plus square root of 3 over 2i. And that's your first answer. What's the second answer? Well, first of all, the second answer is 1, right? If you turn 1 into itself, you're going to get 1. If you turn this at a 240 degree angle now, so every multiples of 120, right? You have 240, 480, 720. Where will it return? It will also return back to 1. it will also return back to this 1 right here. And therefore, that's also a valid answer, which is 1 cosine of 240 instead. So that will be still 1 minus 1/2, but minus square root of 3 over 2i. So those are our roots of the cube root of 1. What about the fourth root of 1? The same rotation applies. How many times you have to rotate to get to 1? Well, it's just simple. It's just how many times you have to rotate 4 times to get to 1? 90, 90, 90, 90. So 90 is one of our answers. So actually, like, it will be really easy if you just look at the graph. If you just look at the graph, you will be able to know what this number is if we were comparing it to the imaginary plane. It's I. And same thing for minus 1. Minus 1, and same thing for this, because when you turn this, you have 270, 540, 810, and then 1080, which will get you back to 1 because it's a multiple of 360, right? So all the roots is 1, I, minus 1, 1, and minus I. See, it works so well, right? I don't know why it's so, it just works really well. That's all I want. So what about you if you want to find the roots of any complex number, right? This is the textbook method of doing it. This is, right? I'm gonna try to use my method of doing it. So the textbook method of doing it is just to basically give you the magnitude, since it's r to the n power. So you have to find the magnitude first, and then you have to take it to the nth root. So whenever you multiply it 6 times, it becomes back to the n, and our magnitude is square root of 2. So the vector that ends up having the vector is square root of 2 times sine of this junk divided plus I times the cosine of this junk, right? So my method's the same thing. I'm not gonna try to do something different. It's basically the same thing for theta as well, but I'm just gonna do it graphically. 4 square root of 3, well, minus 4 square root of 3, so minus 4 square root of 3 will be right there, and then 4 will be about right there, right? So since we know this is minus 4 square root of 3, and we do know that this is 4 minus 4 as well, you can just tell right then and there that this is going to be 8, right? This is going to be 8, so you're gonna have to take the 6th root of 8 to find your r, which gives you square root of 2, and this is also 30 degrees, and this is also 60 degrees. So what's the angle of this vector? What's the angle of this complex number? It's just going to be this whole thing, which is 30 plus 180, which is 210. 210 degrees. So 210 is 7 pi over 6. And how are we going to know the other vectors that also work? Well, we're going to know the other vectors because if you think about it, if it's a 6th root, how many times you got to turn in order to get to 360? I don't know. What is the degree measure that you need to turn to get to 360 with a 6th root? When you turn 6 times, it's 60 degrees. So the 60 degrees is 60 degrees will give you a pi over 6 boost. No, pi over 3 boost. I mean pi over 3. So you can just put the pi over 3 in k, and that's it. That's your angle, which is exactly the same as. Is it? Yeah, it's exactly the same as this angle. Actually, I don't know why I put Actually, yeah, it is over 6. So I'm actually a little bit mistaken. Pi over 3 is correct, but 7 pi over 60. If you have this 7 pi over 6 right here, this is the 210 is the one that you want. 210 is the angle that you want, so you have to divide by 6 to get 35 degrees. The 35 degrees is the initial vector that you want. Whenever you rotate it 6 times, you will get yourself this vector right here. So the actual answer is 7 pi over 36 plus pi over 3k. I am sorry. This is the correct answer. Correct, right? Okay. So the final question is find all the roots, the 12 roots of. Actually, I'm not even gonna do this last question. This last question is it's easy, but I'm not doing it. Find all 12 roots of unity. Roots of unity means root of 1. So what's the 12 root of 1? 12. How many times you gotta turn? What's the turn that you gotta do to get to 360 degrees? It's 30 degrees. If you want to do it 12 times, it's 30 degrees. So I'm gonna draw this circle right here. Terrible circle. Terrible circle. Terrible circle. Decent circle. Okay, so 12. So if you turn this 30 degrees, 12 times 360. This 60 degrees, you'll get 720, but it'll also go back to the beginning. 1080, also back to the beginning. Back to the beginning, back to the beginning. It keeps going and keeps going. And you can actually find these points on the unit circle just by the trigonometry from chapter 4. This will be 30 degrees, so this will just be the square root of 3 over 2, 1/2. This will be 1/2 square root of 3 over 2. This will be 1. So all of our points are going to be they are going to be plus or minus I. They are going to be plus or minus 1. They are going to be plus or minus 1/2 plus or minus square root of 3 over 2I, and plus or minus 1/2 plus or minus square root of 3 over 2 plus or minus 1/2 I. And those are all your answers for your 12 roots of unity. You can test all of them. They work. They all work. So that's going to be it for today's review. I think that lasted an hour 21 minutes. You guys really should just post in the comments to tell me to do shorter reviews. I tried to make it as short as possible. Didn't succeed. Kind of sad, but I'm pretty sure that the next one will be shorter because it's all about matrices, and I hope that I'll put timestamps on what to do with this review, and I hope that you have learned something from this review, or I hope that you pass your next test or exam. So until next time, I'm going to go. See you later.